Well, hello there, and welcome to Antelope Island State Park in northern Utah. This is the largest island that sits in the Great Salt Lake here in northern Utah. Right now we're looking east at the Wasatch Mountains, this big imposing set of mountains that forms the eastern edge of the Bison and range, mountain range that was uplifted by a large normal fault which runs along the base of the mountain front. And we're out here on the east side of Antelope Island on a beautiful spring day to learn a little bit more about the geology here and what these rocks can tell us about this area's history, looking at the rocks themselves, looking at their characteristics. Thanks for joining me. I'm Geology Professor Shawn Willsey, and our objective today is this is going to be a four-part video series with the idea of working our way up this ridge behind me, because this ridge nicely exposes four discrete sets of rocks, all of which tell a fascinating tale about this region and its geologic history. And so in part one, we're going to focus on the rocks here at the bottom part of the hill, the rocks that are surrounding me. In part two, we'll be up near the skyline there looking at some different rocks that are quite a bit younger. And then right above them, that'll be part three. And then finally, we'll end up just beyond the ridge, but along the spine, more or less, of this island, looking at some rocks. Our journey here today, from part one to part four, is going to take us from these rocks, which are about 1.8 billion years old, from a time period called the Proterozoic, up into parts two and three, where we'll look at rocks from the last part of the Paleozoic, what's called the Neoproterozoic, about 720 to 650 million years ago. And then finally we'll be just beyond the top of the ridge there, looking at rocks that are Cambrian in age, about 500 to 550 million years old. So our journey is going to take us through 1.3 billion years of Earth's history, and we're going to see quite a bit of diversity, not just in the rocks themselves, but in the stories they have to tell. So let's start with these rocks that are surrounding me here, and this is as good as any. We can start with this little boulder right here. And these rocks here that we're looking at that are from the Proterozoic 1.7 to 1.8 billion years ago, these rocks are what we call basement rocks. They are the oldest rocks in this part of North America. They form the oldest rocks. If you think of rocks as sort of a stacked up sequence of rocks, these would be at the bottom of the stack. To see rocks of this age or comparable age or type, you would need to go to the bottom of the Grand Canyon, where similar rocks exist, or in uplifted mountain ranges like the Wasatch or the Tetons, you can see rocks like these as well. So let's start with this one here. We can see this rock is distinctly layered. It looks like it's made out of crystals rather than grains of sediment or organisms. And so with this pronounced mineral layering here, it has all the characteristics of a foliated metamorphic rock, because it has these alternating light and dark layers where the lighter colored minerals and the darker minerals are somewhat segregated. This would be a rock called gneiss, G-N-E-I-S-S. And these rocks have been featured in my Rock Identification with Willsey series. So if you're interested in learning how to identify rocks a little bit better on your own, you might look to that series on my YouTube channel. So it looks like this unit here, these 1.8 billion year old set of rocks, contains quite a bit of gneisses. Let's see what other kinds of rocks we can find. These rocks, these gneisses, are among the high-grade metamorphic rocks that we find, which means that these rocks formed under tremendous temperatures and pressures. And in order to get temperatures and pressures this elevated, you would need to have these rocks be buried very deeply. So not only were they probably squeezed by colliding plates or two continents colliding, but they were also very likely at high temperatures because they were buried so deeply, tens of miles possibly beneath the Earth's surface. Here's something a little different over here. So if we come over here and take a look at this material, it's obviously different in color. It's a lighter color. We don't see the distinct banding in it. In fact, we see that it's more or less kind of a hodgepodge mixture of light colored material mostly. Mineral wise, we can identify a lot of this has a lot of quartz in it. So there's this grayish shadowy material is quartz. Looks like there's also some feldspar in here. So these crystals that have these flat reflective surfaces are feldspar crystals. And then it also looks like this rock has these, I guess, BB size, somewhat reddish brown, although they weather into a little bit darker color here. These are crystals of garnet. So we have some garnet crystals in here that form these little red and dark colored specks throughout the rock. And what we have here then, this is actually an igneous rock. The texture is that of an igneous rock with these larger crystals. This is what's often called a pegmatite. And pegmatites are similar fundamentally to granites in that it's magma that cools underground. But in this case, the crystals grew quite a bit larger than what we'd see maybe in a typical granite. And so this is, a lot of times this is because of water or fluids that are also present within the magma system. But this is a large pegmatite dike, and we can tell it's a dike because here you can actually see it cutting across the rock layers. You can see a sharp contact right here between the brown gneiss, the metamorphic gneiss, and then the rest of this dike. So the dike itself is maybe, oh, I don't know, about 2 or so meters wide. We can see more dark rock on this side, so that looks like that's more or less the edge of the pegmatite dike. And we might be able to trace it out across the landscape as well. So we've got metamorphic gneiss, pegmatites, which represent magma moving through these rocks. Let's see what other rocks we can find. Here's another great example of the gneiss right here, the banding in the gneiss, and then again a nice sharp contact here, and then the pegmatite material as well, this white. And here the garnets are quite a bit larger. You can see the outline of this reddish material here. So pretty fascinating. There's just so much diversity in these rocks. So this is a unit called the Farmington Canyon Complex. Again, it's the same as what you'd see at the bottom of the Grand Canyon, although the names are different. The rock ages and overall rock types are somewhat similar. Here's something a little bit different. So here we have a rock that, hopefully you can see the nice shiny crystals in here. These are all mica crystals, and these muscovite and biotite mica crystals are forming a layered surface here. That's why it's so reflective. And because we have mica as the dominant mineral, this is a metamorphic rock called schist. And so we can see the foliated surface here. Schists are also fairly high temperature, high pressure metamorphic rocks. So schists and gneisses and pegmatites forming all these scrubby outcrops and boulders here in the Farmington Canyon Complex, these 1.8 billion year old set of rocks. So we'll work our way up now for part 2. So please join me in the next section when we head up the hillside here and look at some of these outcrops that are capping the ridge. I think we'll see that they are quite a bit different from these very ancient and incredibly high temperature pressure metamorphic and igneous rocks. These rocks actually formed when a large supercontinent named Rodinia was starting to form. Continents and fragments of continents were coming together and colliding, and as the crust was thickened, these rocks here would represent some of those rocks that were at the very deep roots of those large uplifted mountain ranges. So just fantastic sequence of beautiful metamorphic rocks. There's some beautiful banding here and the gneiss. So we'll go ahead and head up the ridge now. So please join me for part 2 of the series when we're up here looking at the next section of rock as we take in all the scenic beauty here on Antelope Island. Okay, we're here on Antelope Island in the Great Salt Lake, a fantastic state park here in northern Utah. And we've come up this ridge. This is part 2 of a 4-part series, working my way up this ridge and making a transect of some of these different rock types we encounter along this ridge here on the east side of the island. This large outcrop just below me here is what I featured in part 1, the Farmington Canyon complex, the metamorphic, highly deformed metamorphic and intrusive igneous rocks that form the oldest rocks in this area at about 1.8 billion years. So we've actually come up the hill, and just as I was working my way up from that outcrop, the rocks changed a little bit. Now, they look somewhat similar in overall color, but those very intensely deformed metamorphic rocks, we don't see anymore here. So I'm going to take you into this next rock unit, and this may be one of my favorite rock layers here on Antelope Island. Not so much because of how it looks or its appearance, but more so the story that it tells. It tells a really fascinating story that almost defies outright logic. So come with me up this hill here. We'll get to some of these bigger outcrops. We can see the rocks are overall dark in color, various shades of gray, green, purples. And let's walk our way up to this exposure of this little cliff face here, and we'll start with some observations and see what we can learn from this. So right away we can see this is very different than the rock we looked at in part 1, in the basement rocks, the ancient Proterozoic rocks. For context, these rocks are much younger. So between that knob that I hiked past just down here and this location, we crossed a major boundary, a major contact between the rocks, an unconformity. These rocks here are anywhere from about 720 to 650 million years, a time period called the Proterozoic, the end of the Proterozoic, and also sometimes called the Neo-Proterozoic. But let's start making some observations here. We can see that this unit is composed of a variety of rock fragments of various shapes and sizes. If we look in closely here, we can see a lot of these may be igneous or metamorphic in terms of their characteristics. If we look at the sizes of them, see if we can find the biggest one I can see here. Just in this outcrop, some of these clasts or particles are approaching, football size. Maybe a little bit larger. There's some other places on the island where they're almost a meter in diameter, 3 feet or so. So we can see that the sizes varies considerably from very small particles to much larger ones. If we focus a little bit on the shape of these particles, they tend to run the gamut. There are some that are somewhat rounded overall, but then there's others. Over here is one that's almost triangular with a real sharp point there. So some are quite angular. So we're seeing a wide variety of classed shapes and sizes. Here's a piece of quartz in here, some more igneous material, just a real hodgepodge mixture of classed sizes and shapes. So we've made some observations here. Let's see if we can come up with an identification of these rocks. Now, using the some of the tools and skills that I've outlined in my rock identification with Willsey series, it'd be a tough call here. If you decided these were all mostly rounded in shape, you would call this a conglomerate. If it contained all exclusively angular particles, we would call it a breccia. And I think we're seeing a mixture here. And as geologists, what we tend to do is, to be a breccia, things need to be pretty much all angular in terms of the overall shape of those rock particles or clasts. So we might be prone to call this a conglomerate. However, this is a special type of sedimentary rock. This is actually called a diamictite. So a diamictite is basically a conglomerate, but one that has a very muddy matrix. If we look at the actual material that surrounds the rock particles, we can see that it's incredibly fine-grained. We can also see that the matrix, or the muddy material, is the dominant component. This rock is mostly this mud-sized particle, and then we have these big chunks in it. It's almost like a chocolate chip cookie, where we've got the cookie dough, the fine grained material, and then that's punctuated by these larger particles, just like your chocolate chips in the cookie there. That's the way these rocks look. Let's walk a little bit further, and then let's see if we can decipher the story here. Now, what makes these rocks really interesting and compelling is that we find similar rocks to this diamictite in other locations in rocks of the same age. So when we look at rocks from the Neoproterozoic, from the same time frame, on all continents we find these same units, and collectively they're telling us a story about a time frame in Earth's history that's almost unprecedented. It's a time frame known as Snowball Earth. Basically, the idea is these rocks had to have been laid down by a glacier. It's the only mechanism that could move such large particles. There's other evidence that suggests this, because there actually are some other processes that might move rocks of this size. But in places, there's also drop stones, which are actually rocks that melt out of icebergs, hit the muddy bed of the ocean or body of water beneath them, and then create a little depression where those drop in. And so collectively, the evidence for these diamictites that we see, these Neoproterozoic diamictites, is that there was glaciers across the Earth at pretty much all latitudes. So if we reconstruct the continents for that time period, we had a large supercontinent called Rodinia, and during this time frame, about 650 to 720 million years ago, Rodinia was starting to break up. It was starting to fragment, but it was mainly concentrated. The land masses were mainly in the low latitudes near the equator, and then a little bit further north on either side. And so again, this idea is of Snowball Earth is that once you get ice forming, so if you think about when you get snow in your yard, ice is incredibly reflective, and so it's something we call albedo. So by allowing ice to encroach further south during a cold time in Earth's history, at some point you can cover so much of the continents with ice that it creates a positive feedback loop. You've covered so much of the land with ice that now the solar radiation hits that ice, most of it reflects back out into space, and that allows the ice to grow further and further and further and sort of perpetuate itself over time. So these Snowball Earth deposits are just really, really fascinating. Only found in, a scattered few locations, but here on Antelope Island, they're spectacularly exposed. There's a few other places in the Wasatch, southeastern Idaho. You can also see these in parts of Death Valley. And then they're found on other continents as well. But we're gonna go look at next, we'll work our way up the ridge. And in part 3, what we'll do is look at the unit that caps this. So for now, we'll sign off with a good view of our diamictites, these Neoproterozoic units, these glacial deposits, as the ice was carrying all these sediments and dropping them along their margin here on Antelope Island. So we'll see you a little further up the ridge here for part 3. Here we are on the east side of Antelope Island, the largest island in the Great Salt Lake in northern Utah, looking east here at the Wasatch Range. This is part 3 of a 4-part series as I've worked my way from the road on the east side of the island up to this high point here. We can actually look up towards the summit, the highest point on Antelope Island, Prairie Peak here to the south. We're up here at the top of the unit that I focused on in part 2. Thanks for joining me. I'm Geology Professor Shawn Willsey from the College of Southern Idaho. So in part 2, we were looking at these deposits here, this diamictite, this sedimentary rock that's an accumulation of large and small rock particles of all shapes and sizes, randomly assorted. And this is evidence for Snowball Earth, a glacial event that, as we go over time, the evidence keeps supporting more and more that we had glaciers covering most of the planet, if not the entire planet itself. We find these same deposits on all the other continents. We're going to look then now at the next unit that sits above this. Now we can see the overall orientation of these units. They originally were sedimentary, and we can see that their layering, their bedding, is steeply tilted to the right, or in this case to the west. You can see that as I swing back to the north here, the bedding planes are aligned more or less in this manner here. So presumably if we move to the left, to the west, we should be able to see the top of this unit and whatever is sitting on top of it. So working our way to the west, another outcrop here of the diamictite. Just verify, yeah, we've got the clasts in here. Oops, dropped my rock camera. Rock particles cemented together. I should point out, while we're out here on Antelope Island, you'll see in places there's obvious dung. These are not from cows. Antelope Island actually has a large herd of free-roaming bison. We might see some in another place, but it doesn't look like they're congregating over here at the moment. But something to be aware of if you come out onto the island. Another beautiful outcrop here of the diamictite with all the different clasts embedded in it. Great evidence for Snowball Earth. And this is pretty much the last outcrop. As we move over here to the west, we see a distinct change in the color of the rocks. Now we've got these pink colored rocks randomly kind of jumbled about here. We do have some outcrop here. Now this unit doesn't form a nice cliff face, and I think as we deduce what this material is, we'll find out why. So let's just come over here to a nice surface and give it some good observations here. So if we look at this closely, it's pink. As I touch it, it's incredibly sharp. It feels really jagged. We can see there's a lot of micro fracturing or grooves in this material. It doesn't look like any sort of metamorphic rock that we've looked at. It doesn't appear to have any of the crystals we might expect to see in an igneous rock. And so it might be a sedimentary rock. Doesn't appear to be made out of sand or mud-sized particles or clasts. And so what this rock is suggesting is that it's possibly a carbonate rock, or meaning it's either a limestone or dolostone. And if you remember my rock series, one way we can determine that is with using an acid bottle. And it looks like it's not really fizzing much, at least to the naked eye, like we'd expect to see with a limestone composed of calcite. But if we give it a little bit of a scratch here and then put the acid on it, I don't know how well you can see that, but it is actually bubbling a little bit. So it is effervescing and reacting a bit with the acid. So it's weakly reacting to the acid. So that tells us this is a dolostone. So this is a carbonate rock, but not limestone. It's actually dolostone. So instead of being a calcium carbonate, this is actually calcium and magnesium in carbonate form. And so this is part of the story of Snowball Earth. This unit sits directly on top of the diamictite, the dark rock we just passed by over here. And everywhere we go around the globe and look at these Proterozoic diamictites, we see these carbonate rocks sitting right on top of them. These are sometimes called cap carbonates. So if you think about it, if the planet was entirely or nearly so covered in ice, at some point you had to break out of that cycle. And so what would that look like? So the idea, the model we have for how these carbonates would form, the model that best matches this evidence is that we still had volcanoes and the heat within the earth accumulating beneath that glacial ice. And so eventually those volcanoes, as they're erupting, they're pumping a lot of CO2 into the atmosphere, carbon dioxide. And as that CO2 would accumulate over time, a lot of the typical Earth processes that might absorb that CO2 out of the atmosphere, those processes aren't taking place because we've got this icy planet at this point. And so by the CO2, the carbon dioxide, going into the atmosphere, that actually is like a blanket. It actually keeps a lot of Earth's radiation from escaping back out into space. So it warms the planet over time and actually produces a greenhouse effect. So eventually you could build up enough heat in the atmosphere that you would start to melt the ice. So now the continents start to lose the glaciers, they become ice-free, and then over time we would then have weathering processes back on land like we would normally have, and those weathering processes now are carrying sediment and other material out to the ocean. So by rapidly and intensely weathering the continents, you could build up the amount of carbonate that's out in the water, and that would deposit these carbonates like we have here with this cap carbonate, this dolostone. And hopefully I got that right. The chemistry's slightly above my pay grade, but I believe that's the model we have for these. So we can see that this dolostone, this carbonate material, isn't hugely extensive here. And this makes sense why it would be pretty weathered, right? It's a carbonate, so it's prone to chemical weathering. When it rains or snows out here on the island, that actually dissolves some of the material. And that's why that outcrop I put my hand on was a little bit rough to the touch, had those little kind of grooves in it, is that's some of the chemical weathering that's going on here. So we've worked our way mostly up the ridge. We've got one more destination to go, which we'll get to in part 4. At some point we might also discuss some of the other cool features on this island, like these shorelines that we can see here from the rise and fall of ancient Lake Bonneville. When this was under a large freshwater body of water, we can see a nice pronounced shoreline just over here looking to the south. So we'll go ahead and head up to our final destination for part 4. Hopefully you've been enjoying these little videos here on Antelope Island, one of my favorite places to be. Oh, and one last thing, there's actually a pit that was dug up here. And I hunted around wondering what would they be actually looking for here. And I think I found the answer. There is here on the dolostone some greenish staining on the rock. You actually can see a darker coating over here. And these look like copper minerals. That's probably chrysocolla, a copper silicate. I don't think it's malachite. I tried it with the acid bottle and didn't react. So possibly someone had at one point saw a little hint of copper bearing minerals and excavated a little pit here. Probably didn't find much more beyond that. So anyway, we'll go head up the ridge and continue on at stop 4. We interrupt your geology programming for a quick look at some of the bison here on Antelope Island. This one's pretty close, but I'm actually in the car, so no worries, at least on my end. But you can see how big these creatures are, and there's this free-ranging herd of bison that live out here in the island. So I'm not sure what this one's doing, if he's scratching himself on the rocks or what. But yeah, driving around on the roads here, you're bound to see a few pretty much any time of year. Okay, back to geology. So we've come up in the last 3 parts to this series. This is kind of the head of this ridge, which drops off a couple hundred feet down to the road and the lake level. The dark rocks on this knoll over here were the diamictites, the dark sedimentary units from the Snowball Earth episode that were featured in part two. And just this side of those dark units, it's a subtle outcrop and it's not very large. In part 3, we looked at some dolostone, some pink dolostone that caps those diamictites and are related to this snowball earth story. We came across this sort of boulder field here, which is along one of the shorelines from ancient Lake Bonneville. And those boulders are actually weathered out of the outcrops that I'm standing on right here. So this is our part 4. We've come up the ridge. We started at the bottom in part 1 in the Proterozoic about 1.8 billion years ago. We arrived at part 2 and 3 looking at some diamictite and dolostone that's about 720 to 650 million years ago. And now we've just crossed another fairly substantial unconformity, and now we're in rocks that are Cambrian in age. So these rocks are about 500 to 550 or so million years ago. Making a few observations here. It looks like they're this tan to beige colored. In places, they contain large, rounded particles, gravel-sized particles, golf ball size in most places of rock. In other places, it looks like it's much more fine-grained, and so the particle size is much smaller. These rocks are incredibly hard and resistant. One of the most resistant rocks that's on the planet. We can also see that the gravel layers actually form distinct layers in the rock. We've got a gravel layer here, then a sort of a sandy interval, then another gravel layer running through the rock, and another one there. Now these boulders around my feet are all eroded, so let's head up to the actual outcrop here, the rocks that are in place, and see what we can glean from these rocks. So again, these cobbles, or I guess gravel-sized particles, cemented in the rock itself. Looks like most of these are pure quartz or quartzites of various colors. In fact, the rock is almost exclusively made out of these quartzite and quartz gravel-sized particles. We would call then this a very mature sedimentary deposit, meaning whatever the source area is, even if it contained mostly quartz, well, if it didn't contain mostly quartz, if there were other rocks present, we would expect that the quartz would break up and sort of pulverize those other rock particles. So by the time we get to this point, we're just seeing the quartz being the primary constituent in the rock. Over here, if we look at the grain size, it's a little more towards the sand size and a little bit maybe pebbly in places. So these are sedimentary rocks. I think we'd all agree that in places where we have these gravel-sized particles, because the gravel-sized particles, their shape tends to be fairly well rounded overall. Some of them are broken like this one, but you can see the overall shape of the class tends to be a little bit more rounded than anything. So I think it would be appropriate to call this rock a conglomerate. Here's one of the bigger class I've seen so far. That one's maybe a couple inches, 3 inches maybe in diameter. But also in places where the gravel is less dominant, we would maybe call it a sandstone. Now the sandstone here has been fused together such that the sand grains are actually binding together, and it doesn't really feel like most sandstones, very gritty. So this is actually a Cambrian unit called the Tintic, T-I-N-T-I-C, quartzite. Doesn't make much sense, but it's what we would call an orthoquartzite. Basically, this was a sandstone that must have got buried deep enough that the pressure of the overlying rocks caused the particles to fuse together such that now when the rock breaks, it doesn't break around the sand grains, it tends to break right through them. The bottom of the Tintic quartzite is a little more gravel rich, and that's why we're seeing so much of this gravel that kind of pops as you look at it here. We look up at this outcrop here, seems to have a hint of bedding. So it looks to me like the rock layer here is gently dipping to the left, which is to the west. There's obviously a large fracture there, but even more importantly, I can see some changes in the particle size. I can see gravel-rich particles up here, and then more of a sandy bed down low. And so this would indicate that whatever was transporting these sediments, the energy level was fluctuating to some degree. At times it had enough energy, high enough energy, that it was moving dominantly these gravel sized particles, these golf ball and almost baseball size particles of gravel. And at other times the energy waned a little bit, such that it was mainly moving and transporting these smaller pebbles and sand sized particles here. These have been studied and analyzed, and based on where the continents were at the time and all the available evidence here, this Cambrian age unit was deposited near the shore of ancient North America. So here in northern Utah, we were actually on the coastline of the North American continent before California, Oregon, Washington, and most of Nevada even existed. So these rocks represent some of the old shoreline deposits that were deposited at that time. We'll walk a little bit further because we're right near the crest of the ridge line here on the island, and a few more outcrops here of this Cambrian age tintic quartzite. But then we get a great view off to the west, looking down into White Rock Bay. This big knob over here is called Elephant Head. Antelope Island, just really great place to recreate. We got someone mountain biking one of the trails they have out here. And most of the island is made of these 3 or 4 rock types that we've been exploring here today. So just in summary, with these 4 parts, we started in part 1 looking at basement rocks, metamorphic, igneous, intrusive rocks formed by high temperatures and pressures, rocks that formed miles, tens of miles beneath a large mountain range about 1.8 billion years ago. We worked our way up the ridge, and in part 2 we saw parts 2 and 3 we saw evidence for a massive glacial event that potentially covered the entire planet between about 720 and 650 million years ago. That was our very latest Neoproterozoic age rocks. And now here at the top of the ridge on this beautiful day, we're looking at these Cambrian aged rocks that were deposited on a beach or a shoreline at the edge of North America about 500 million years ago. So just consider how much geologic change it would take to go from the underbelly of a mountain range, the rocks we saw in part 1, to surface glaciers carrying large rocks for parts 2 and 3, to finally having this quiescent shoreline of North America where we had streams flowing into it, wave action that was moving around the gravel and the sand and depositing it to form these deposits here. So hope you've enjoyed this little series here. This was a real pleasure for me because I have great memories of Antelope Island. I did some undergrad research here. Just fun days recreating out here. It's one of my favorite places, but make sure you come either when it's sufficiently windy or not in the heat of summer, because there are some bugs out here that can make your day pretty grueling and somewhat miserable. But in the winter time, in the early spring, or in the late fall, it's just a magical place to be. And so I hope you enjoy it. As always, if you can donate and support the videos and content I produce, it would be much appreciated. There's the donate button on the banner of the YouTube page, a thanks button at the bottom of the screen to the right, and under the video description there's also some information there if you can help support my geologic exploits and sharing some of Earth's amazing geology and landscapes with you. So until next time, we'll see you from Antelope Island State Park in northern Utah.